Hey everyone, it's Mr. Glover here. So today we're going to talk about radians. This is a big topic. This is something that I wanted to make sure we cover before the year ends, because if you were planning on studying more math, this will come up, and this is an important concept to know about. In a nutshell, radians are another way of measuring angles. They're more exact because you typically will use fractions rather than rounding decimals, but we'll get into that once we've built up our theory around radians. So to start out, we're going to take a look at something called the arc length of a circle. The arc length is like the distance around the outside of a circle that you would trace if you were to go through a specific angle. So technically speaking, you would say if you subtend an angle of 80 degrees, what's the arc length? We haven't really thought about this before. Many of you probably haven't even considered this concept, but there's got to be some way to find the arc length on the outside of a circle, not just a direct triangle using Pythagoras. And it turns out there is. So if you remember, a circumference is given by the formula 2 pi r. In this case, r is 5, because we have a radius of, we'll go with a radius of 5 meters. So our circumference is going to be 2 times pi times 5. We're going to end up with a circumference of roughly 31.4. And I suppose that would be in meters. All right. So then our arc length is going to be a portion of it. And you've got to think about what ratio of the whole circle we're talking about here. If there's 360 degrees in the whole circle, we've only traveled 80 of it, well then we've basically gone through 83/60ths of the circle. So we can say our arc length is equal to 80 over 360 by 360 times 31.4, and we end up with an arc length of 6.98 meters. That's basically the thought process. We've got to think of the ratio of the circle that we're traveling around, and we multiply that by the whole circumference. In a slightly more elegant formula, we can write the formula by comparing ratios. So we can compare the sector angle divided by the entire circle, so it's 360 degrees. And this will equal arc length divided by 2 pi r, or arc length divided by circumference. So this is our formula we can use to calculate an arc length at any point in time. And typically, your sector angle is just going to be given to you, so that's a number, and arc length is the variable you're trying to find. But you could technically find any of these. So now let's focus on a very specific situation. We're going to focus on the situation where the arc length is the same as the radius. And the question becomes, what angle subtends an arc length that's the same as the radius? So let's take our formula that we just built and let's use it. So we've got theta over 360 equals arc length over 2 pi r, right? And now the arc length is 5 and r is 5, so we can fill in a little bit of this fill in a little bit of this formula. Theta over 360 equals 5 over 2 pi times 5. And now we can cancel out the 5s. We can also multiply by 360. So theta equals 360 times 1 over 2 pi. Or theta equals 360 over 2 pi. And if we put this in a calculator, we end up with an angle theta of 57.3 degrees, roughly. That's 1 radian. So radian is a much larger chunk of our circle than a degree is. There's 360 of degrees in a circle. There's 2 pi radians. So a radian is a relationship between arc length and radius. You can define an angle in radians as arc length divided by radius. So if you're trying to find an arc length, Working with radians is a lot nicer. If you are working with, if you're working with degrees, you have to use this formula. Angles can be measured in degrees, circles 360, or in radians. There are 2 pi, which is roughly 2.6 or 6.28 radians in a circle. So this is important. This is significant because we've actually talked about what pi is. Pi is the number of arc lengths in half a circle, or 180 degrees, or sorry, number of radians. 2 pi is the number of radians in a whole circle. So that's what pi is. That's why it's such a significant number. It's a special number that it's a irrational number that continues forever, but we can approximate it. And usually we use 3.14, but if you're doing any calculations, use the pi button on a calculator. It'll be more accurate. It will have more decimal places. So let's compare a degree to a radian. A degree is like a very, very thin slice of the pi. So a degree is going to be something like that, compared to a radian, which is going to be something like that. And let's talk about some situations. So we'll talk about a whole circle. We'll talk about half a circle. And we'll talk about a quarter of a circle. So for an entire circle, we've got 360 degrees, but we have 2 pi radians. For half a circle, we've got 180 degrees, which is pi radians. And for a quarter of a circle, we've got 90 degrees, but we have pi over 2 radians. To convert between degrees and radians, we just need to use one of these ratios. Use whatever one you like the most. Usually, people will use the fact that 180 degrees equals pi radians. But you could do 360 and 2 pi, or you could use 90 and pi over 2. So let's go through some conversions. We have 30 degrees. What we're going to do is kind of like stoichiometry that you would do if you're taking chemistry, where you're converting units. We know the ratio is 180 to pi. We need to write the fraction so that our units cancel and we're left with the ones we want. So I'm going to go 30 degrees times pi over 180. Pi is in radians, 180 is in degrees. And what we end up doing is we can now cancel out the degrees and our units are in radians. If you were converting from radians to degrees, you'd be multiplying by 180 over pi. So 30 times pi over 180 works out to pi over 6 radians. That is a number that you will see many times. Minus 120, we can do the same sort of strategy. Negative angles are still angles. So 120 over 1 times pi over 180. Technically, it's degrees and radians. I'm probably not going to write that every time. The degrees will cancel, and you'll be left with negative 2/3, or negative 2 pi over 3. Radians. We can keep doing this. We'll do it a little bit quicker because we're basically using the same process for all of these. So 5 pi over 4. This time we're just going to multiply by degrees over radians. So this we're going to multiply by 180 over pi this time. Radians will cancel. 180 over pi times 5 pi over 4 is 225 degrees. 2.57, same thing, just multiply, I guess this could be written over 1. We're going to multiply by 180 over pi. This is 147.25 degrees. And we've got a few more. You can try these on your own. Pause the video, give it a shot yourself, but I'll run you through them quickly. 60 times pi over 180 equals pi over 3 radians. Negative 270 times pi over 180 is negative 3 pi over 2. Converting to degrees, 2 pi over 3 times 180 over pi gets me 120 degrees. And 3.45 times 180 over pi gets me 197.67 degrees. And so you might have noticed a trend here. I have left my degrees in decimal form, but I've left all of my radians in fractions. And you might be wondering, like, well, why don't we just divide pi over 6? Why don't we just punch it into our calculator and write down 0.52359877756? And it kind of comes back to the whole point of why we use radians. You'll find later on math that radians allow things to cancel. Specifically, things like pi will cancel. And what you're doing is every time you're able to cancel out an irrational number like pi, it's gonna mean less mistakes or less rounding errors later on. Because every time you have to multiply by pi, you're gonna cut off that digit somewhere. And so if you can leave things in fractions, then your answer is an exact answer. As soon as you go to calculate it, then it's no longer exact. And with degrees, you're going to end up rounding more often. So you're going to end up with more error unless you carry infinitely many decimal points. So radians allow us to work with very exact things, and you will find that it also allows you to do some elegant tricks in math where you can cancel things out that you otherwise wouldn't be able to. As we did before, we can find the trig ratios, trigonometric ratios of angles and radians. So we've got a couple things to keep in mind here. Now that we've got two measures of angle, you have to sort of stop and think before you start a question. Am I working in radians or am I working in degrees? Okay, so if you're working in degrees, you need to make sure that your calculator is in degree mode. And you can set the mode on a TI calculator. It's usually next to the yellow second button. It's called mode. You go down and you'll have an option between radians and degrees. So if you're working in degrees, then use degrees. If you're working in radians, select radians. But you might not know when you're working in radians because it doesn't always say rads. If you see pi, then you're working in radians, almost always. And if you see the degree symbol, you're working in degrees. So usually radians will involve pi. So let's talk about approximate versus exact values. We want to find the approximate value of cosecant 2 pi over 3. So we've got to go back to what cosecant is. So we know that cosecant theta is 1 over sine theta. There's no cosecant button on most calculators. I know it's tempting to want to hit the cos minus 1, but that's not cosecant. So you need to actually find sine and divide it 1 by it. So cosecant of 2 pi over 3 is actually 1 divided by sine of pi over 3. So you basically, what you do is you calculate sine of pi over 3. And then you can actually carry your answer. So you can go 1 second, or 1 divided by second answer. And you'll get 1.15. If you aren't comfortable carrying your answer, you can just use a rounded digit. But the more times you round, the more mistakes you'll make. And you'll find that things will be off by like 1 or 2 decimal places sometimes. So if you have an exact value, all you really have to do, or sorry, if you have an approximate value, all you really have to do is plug the numbers into your calculator. If you have an exact value though, then you can't just plug your numbers into your calculator, okay? When you have the word exact, that's a hint that you need to use a special triangle. And now we talked about 2 of them yesterday. We're going to talk about the same 2 today. So there's the 30-60-90 triangle, which I'm doing an awful job of drawing, but pretend that it's nice and to scale, which it isn't, but okay, let's just do this again. Okay, let's say that's our 30, 60, 90 triangle. And let's say we also have our 45, 45, 90 triangle. Okay. We can draw these in radians. So I suppose I should zoom in a little more. So let's label the outsides first. We've got 1, 2, root 3. And we have 1, 1, root 2. Okay. So this triangle was 45 degrees, 45 degrees, and 90 degrees. All right? 90 is pi over 2. So these are both pi over 2. If you have pi radians in 180, half of that is pi over 2. 45 degrees is pi over 4. So this triangle is the same, but it's now got radians instead of degrees. Instead of 45, we have pi over 4. This one's the same kind of idea, but we have to convert 30 and 60 to radians. 30 is going to be pi over 6. That's going to be across from the smallest side. And pi over 3 is going to be 60 degrees. All right, so when you see exact, you should draw these triangles and you should look at the number you're given, and it's likely going to have a reference angle of pi over 6, pi over 3, or pi over 4. Or maybe pi over 2, I suppose. Problem with radians, and the reason why people struggle with them in high school usually, is because you need to use fractions, and the fractions involve pi's, and doing the algebra is a little bit more tedious, a little more arduous. Anyways, determine the exact value of tan 7 pi over 3. So we need to remember that half of a circle is pi. So half a circle is 3 pi over 3. So that means one full rotation is 6 pi over 3. So minus 7 pi over 3 equals negative 6 pi over 3 plus negative pi over 3. This is like one whole rotation, and this is what's left. So basically what we've done is we've gone pi over 3 past full rotation. So I'm going to draw this out. Hopefully this makes it a little bit less confusing. We're going to start here. We are going to rotate around the circle. That rotation is 2 pi radians, or sorry, minus 2 pi radians, which is minus 6 pi over 3. We're going to keep going to about here. Well, maybe not quite that far. A little bit there. And we're going to draw a ray. In standard position, this is negative 7 pi over 3. So theta is negative 7 pi over 3. Okay. But what we don't have is the reference angle. And the reference angle is negative pi over 3. So this is our reference angle of pi over 3. Technically it's negative. We've got a special triangle for pi over 3. The opposite to pi over 3 is root 3. The adjacent to pi over 3 is 1. And the hypotenuse of this pi over 3 triangle will be 2. We can fill in what we know when we know that this is a negative side length. But using special triangles, we now have all the pieces for our special triangle. It's kind of a weird concept, but because I know it was an exact value, I knew I would have a reference angle of pi over 3, pi over 6, or pi over 2, or pi over 4. I looked at what I had, I drew it out, and I found it's pi over 3 is my reference angle. So I can literally take the numbers in my special triangle, and I can just throw them in this unit circle. And you're probably wondering, well, how do I know this is 2, 1, and root 3? Well, I don't. But I know that the ratios will always cancel and simplify to this. I could make twice as big of a triangle, and it will have twice as big of an x value, and twice as big of a y value, and twice as big of an r value. But when I divide x over y, or y over r, those magnitude 2, or not magnitudes of 2, those multiples of 2, those are just going to cancel out, so it doesn't matter. You can just slap the unit circle, or special triangle, right onto the unit circle. And actually, what I normally do in this unit is I get you to build one with a string and a piece of paper. You mark down all your special triangle angles. So you mark down 60, 30, 90, 45, all the way around the circle. And then you literally build one of these. One side of it's going to be in radians, one side of it's going to be in degrees. So if I give you an angle, you can just rotate your ray towards it, place it in position, and then slap this triangle down that you know fits, and you've got all three sides. Okay, so we're tasked with finding tan of this angle. So tan of minus 7 pi over 3 is given by the formula y over x. Okay. Y is negative root 3, and x is 1. So this is given by negative root 3 over 1. So that means tan of negative 7 pi over 3 is literally just negative root 3. If you take your calculator and it's in radians and you tell it to calculate tan of minus 7 pi over 3, you'll get negative root 3. That's what your calculator's doing. Well, it's probably doing an algorithm that's not quite that, but that's the logic of where this number comes from. All right, let's try a similar question, but this question involves a point instead of give a specific angle. We're given a point minus 9 and 5, minus 5, terminal point of the angle theta in standard position to the nearest tenth of a radian. Determine the possible values of theta. And we're given a domain. Don't worry about the domain yet, because what we're going to find is we're going to be drawing a ray, and then that ray is going to have angles attached to it. This tells us how many angles we're allowed to give as our answer. So let's draw this point first, minus 9 and minus 5. So draw our grid. Minus 9 and minus 5 is going to be down here somewhere. So we're going to have a ray that looks like this. Technically, this is point P right here. We will have a y value and an x value, and we can just label those. We know what those are. This is minus 9. This is minus 5. Okay? And now, we could find r, but we don't really need it. We're not doing the trig ratios. We need to find our angles. So what we actually need to find is we need to find our reference angle. We need to find this value. You can call this phi or alpha. Let's call it alpha. This is just a different angle. I don't want to call it theta, because I don't want it to be confusing. And so we can use normal trigonometry that you've done for years, SOHCAHTOA, which is literally just trig ratios with different labels, to figure out what alpha is. I know that I have the opposite side and I have the adjacent side. So let's use tangent. You could solve for r using Pythagoras, and then you could use sine or cos, but I don't want to do more work. So I know that tan of alpha is minus 5 over minus 9. Okay, so I know that alpha is arctan of minus 5 over minus 9. And as long as my calculator's in radian mode, I can just plug this in. And I'm going to get my reference angle. I'm going to get a reference angle alpha of 0.507. I suppose I should round it to 1 or 2 decimal places, but I'll keep it exact until the very end, right? So here's the thing. Now that we have alpha, we can build our two angles. I have the option to go from 0 to 2 pi, so I can pick an angle anywhere from here all the way around back to this x-axis again. So I know I have one angle here, called theta 1. I also know that I can go from 0 backwards to negative 2 pi. So I can rotate around in the opposite direction. I can go all the way this way until I get back to the x-axis. So I also have an angle here, call it theta 2. Those are my standard position angles. Those are going to be what the question's asking us for. So I can find theta 1. Theta 1 is simply going to be pi plus alpha. That's because pi is halfway around a circle and we're alpha units past that. So this is going to be pi plus 0.507. And I'm going to get an angle of 3.65 radians, which is about 3.7 radians to the 10th of a radian. So that's theta 1. And theta 2 is going to be pi minus alpha. We're not quite to pi. We haven't made it all the way back to the x-axis with alpha short. So theta 2 is going to be, actually, technically it's minus pi plus alpha, which is kind of weird, but it's going backwards, so it's negative angle. This is going to be minus pi plus 0.507. We'll end up with negative 2.63, so we'll call it negative 2.6 radians. And there we go, we're done. So it's kind of weird, and I know that the questions are confusing, but they have to be. There's infinitely many angles that are attached to this. If I just ask you, find all angles that match this ray, then there's no way to do that unless you give me a really general answer. But if I give you this specified domain, then that limits you to only being able to measure positive angles up till 2 pi and only measuring negative angles up to negative 2 pi. Let's try one more question. So we can use arc lengths and radians to solve problems. A centered pivot irrigation system traces out a circular path as it irrigates farm fields. One system has an arm length of 36 meters. The speed of the end of the arm is 3 meters per minute. Okay. In radians, through which angle will the arm have rotated in 30 minutes? Okay. So let's draw the diagram first. So we've got this pivot, we've got this arm. The arm I know is 36 meters. So I know that the arm is 36. It's going to trace a path. And it's eventually going to end up in position 2. It's still going to have an arm length of 36 meters. But what I don't know is the arc length. I know that at the end of this, I'm rotating at a speed of 3 meters per minute. And I know it's going to follow this sort of arced path, okay? So we need to kind of put everything we have together. We know the speed of rotation, and we know that it goes for 30 minutes. So 30 minutes times 3 meters per minute means that this will rotate through 90 meters. So I know that this arc length is 90 meters. That's the distance from over here all the way over here. And so now we've got all the pieces we need to find our angle. Because we're working with radians, this is much nicer. We don't have to use the ugly formula. We don't have to use this one. We can simply use this one. So theta in radians is arc length over radius. So in radians, this is 90 meters over 36 meters. And I have an angle theta of 2.5 radians. That's quite useful. Now I can figure out how long it's going to take to trace the entire path. I can also figure out at what point in time I'm going to reach a specific part of my farm. If you model it using trigonometry, then you can find out a lot of information just from this. So here's a little bit of a tricky question. To the nearest meter, how far will the end of the arm be from the starting point? So let's draw this diagram again. It's basically the same thing, but it's all cluttered on the other page, and I want to make it a little bit easier to read. So we've got this kind of situation. This is 36 meters, 36 meters. This is 2.5. And we want to find this distance. All right, so this is probably bringing back nightmares of pre-calc 11. This is a side angle side triangle. We need to use the cosine law to solve it. So we can pick any flavor of the cosine law we want. A squared plus b squared minus 2ab cos c equals c squared. So we can just relabel whatever sides. It doesn't really matter. I'm going to use this sort of standard version, but we're going to use the cosine law. I hope your teacher didn't teach you 3 different versions of it last year. There's really just the one, and it depends on sort of what sides you're talking about. You can rearrange it to solve for different versions, but you don't need to memorize 3. So c squared equals a squared plus b squared minus 2ab cos c. And I should probably be careful. This is going to be a capital. And by the way, this is just a Pythagorean theorem. This is a squared plus b squared is c squared. The only thing is that 2ab cos c allows you to use it for any triangle. If c is 90 degrees, this term is gone, and you just have the regular Pythagoras. But now we can generalize it to any triangle, and we're not stuck with only right-angled triangles. Okay, so let's put in what we know. I suppose we should probably label our sides. Call this side C, A, B, and this will be angle C. So that means C squared, or C equals the square root of A squared plus B squared minus 2AB cos C. Put in our numbers. C equals the square root of 36 squared plus 36 squared minus 2 times 36 times 36 cos 2.5. And before you put this in your calculator, make sure that your calculator is in Radian mode, or it's not going to work. And you end up with C equals 68.3 meters. And we're done. So there's an application of the cosine law from last year. If you took Physics 12, you'd see lots of applications in static equilibrium unit, but if you're not taking that, you might be wondering why you spent all that time learning it last year. So that's where we're going to stop things. We've talked about quite a bit, a lot of new ideas. The big thing I want to hit home with is that radians are another measure of angles, and you will find that they're more elegant, but they're a little bit more tedious to work with. You have to deal with fractions of pi, and that's a lot uglier than dealing with like 70 degrees. But when you get a handle on them, they do make your life easier later on if you're going to study more. So I've got a few questions for you to try. If you've got some time, give these a shot. Let me know if you need some help. But otherwise, I'll end the video, and hopefully everybody has a great rest of the day. Bye for now.